Welcome to this video in the kinetics unit. It is unit 14, and this short video is going to dive into potential energy diagrams and how to navigate them. If you haven't already done so, please download and print out the blank potential energy diagram companion worksheet. It's going to look like this and gives you spots to take notes directly from this lesson onto here. You can also annotate the model or the sample potential energy diagram with what you are learning about. You also may need a calculator, and you most certainly are going to need a pencil. So without any further ado, let's get started. So what are these potential energy diagrams anyway? Well, at their heart, and there are two examples down here, they're essentially graphs. And they are graphs that are going to follow the energy changes that are occurring as chemical reactions proceed. We will specifically be focusing on the potential energy of the system as our reactants get turned into products. So the first thing I want to dive into is talking about being able to tell whether a reaction is in fact endo or exothermic by looking just at the potential energy diagram. And one of the things that we have to take into account is the fact that when you have an exothermic reaction, that means that that reaction has released heat energy, which means it's going to have less energy in the products than it did in the reactants. You'll notice that this top graph that's right here represents an exothermic reaction. Notice that my reactants have much higher energy than the products, so that means over the course of this reaction, our products have lost energy. Conversely, the endothermic reaction, we see the products actually have more energy than the reactants did. Now, how did that happen? Well, from somewhere, from some surroundings or something that happened, the reactants actually picked up energy, and their products are at a higher potential energy level than the reactants were. So the key to telling endo from exo is looking at the position of reactants versus products. If the products are lower, that means we lost energy and energy was released, exothermic. If we actually have products with more energy than the reactants, it means energy was absorbed, and it's endothermic. All right, now that we got endo and exo out of the way, let's dive into all the various parts of the potential energy diagram and what it tells us. And we are really going to look at this with a qualitative lens, but we will throw some quantitative in there to help you understand what you're seeing. First thing you have to understand is that your reactants live here on the left-hand side, and eventually over the course of a reaction, your reactants come together and make products. But they don't do that immediately. They actually, at some point right here at the top of the curve, form what is called the activated complex. And the activated complex is essentially a transition state. Some people would call it an intermediate between reactants and products. It's almost where the reactants haven't quite formed products, but yet they are not looking like they are reactants yet. The best way I can describe that is if you look at the products, which are here, you can see that the products are a red circle and a blue circle, but yet the transition state, or our activated complex, doesn't look like either the reactants or the products. So activated complex is the new item that you probably had never heard about, but now know about. So make sure that this makes its way onto your companion worksheet. The next thing I want to dive into is how much energy your reactants, activated complex, and products have. And we're going to look at this qualitatively and quantitatively. Now, remember, this is a graph. So when we want to talk about the energy of the reactants, if we said label that with an arrow, well, your arrow you want to put somewhere on this potential energy diagram to show how much energy the reactants have. And if you look at the y-axis quantitatively, you can see the reactants have about 100 kilojoules worth of energy. So if I wanted to show that with an arrow, I would drop that in from obviously the x-axis all the way up to that 100 kilojoules. And that's what's referred to as the potential energy of the reactants. Same thing with the potential energy of the products. If they said label that with an arrow, we would want to go from the x-axis up to the point where the products are, and we would see the products are at about 50 kilojoules. So we would label with an arrow like that, and if we wanted it quantitatively, we would say the products have a potential energy of 50 kilojoules. And there's one spot that we haven't talked about yet, And you guessed it, it is the potential energy of the activated complex, our transition state, our intermediate. So if you are considering what that would be and you wanted to label it with an arrow, you would put it from the x-axis all the way up to that activated complex. If I wanted it quantitatively, I would say the energy or the potential energy of the activated complex is 200 kilojoules. Now that we've talked about the energy of the reactants, products, and activated complex, we're going to get into what's called the activation energy. This is an important concept. And if you remember from a previous lesson, activation energy is the minimum energy that's required to initiate a chemical reaction and have it proceed on its own. I give you here a roller coaster. Everybody knows that when you first get on a roller coaster and you strap yourself in and get seatbelted, you guys have to go up this giant hill that's pulled by a chain. Now, you can't get up that hill on your own. It's the chain that's pulling you. But once you get to the top, the chain releases you, and then the ride takes off on its own power. Here's an example illustrating this fact. It's a very famous roller coaster from Japan. Check this out. So we are looking at video of a gentleman on this roller coaster who's taking GoPro footage. I'm going to speed this up a little bit. And you'll notice that the chain is pulling the roller coaster cars up. And they're at the top, and there's still the chain. And then all of a sudden, the chain lets go. And now the roller coaster is proceeding on its own. So you may be thinking, well, what exactly did that roller coaster have to do with activation energy and potential energy diagrams? Well, if you think about it like this, and we look at this potential energy diagram here, you could see energy had to get put in to get to that top spot there, and then the reaction proceeded on its own. And you'll notice when energy comes in here, this is now called the activation energy. Looking at this a little clearer, you could think of it, since we know activation energy is the energy that is required for a reaction to now proceed on its own, it's almost like saying, well, how much energy does this reaction currently need to get me to the top of the hill, to the activated complex, so it can proceed on its own? And one thing you know is that the reactants actually have energy already. They are coming in with 100 kilojoules worth of energy, but they really need 200 kilojoules to reach what's up here. So the activation energy is this distance from here to here. And if we were to label it with an arrow, it would look like this. If we were to do it quantitatively, our activation energy, and we're calling this the forward activation energy because we're proceeding left to right, would be 100 kilojoules. Now, I made a distinction calling this forward activation energy. You guessed it. That means there's reverse activation energy. You guys are going to find out in this particular unit that there are reactions that can proceed forward and then proceed in reverse. So if I wanted to know what the reverse activation energy, that's like saying instead of going reactant to product, I'm now going product back to reactant. Well, how much energy do the products have? They got 50 kilojoules about. And what do I need to initiate that reaction? I need 200. So my reverse activation energy is actually 150 kilojoules, and we can label that with an arrow. It is that distance from the products to the activated complex. It is a robust 150 kilojoules. So the reverse activation energy is higher than the forward, which means probably, as we're going to see later on, it's a little easier for this reaction to proceed in the forward direction. And that'll be relevant later when we get into the equilibrium chapter. So the next thing that I want to get into coming off activation energy is our delta H, otherwise known as our heat of reaction. It's our reaction enthalpy, or the net change in heat over the course of a reaction. You have seen this most notably on table I on your CSERT, where there was a giant list of things that were endothermic, exothermic, and just how much. Let me give you a little bit of insight into how delta H is calculated, and we are going to use this existing potential energy diagram that we see here. Now, the first thing you guys are going to notice is if I asked you, is this endo or exothermic, you're going to say, well, the reactants have more energy than the products. Got to be exothermic. And I would say you're 100% right. If you think back to table I on the CSERT, all your exothermic reactions had negative delta H's. Well, how did we come up with that? Well, this isn't quite a lesson on Hess's law of heat summation, but this is a much quicker way to handle the overall change in heat of a reaction. You guys have to know this formula. The delta H is equal to the heat of your products minus the heat of the reactants. And looking at this potential energy diagram, we can pick that out right away. We can see our products actually have 50 kilojoules worth of heat. So the potential energy of the products is 50 kilojoules. The potential energy of the reactants is 200 kilojoules. So I want to now plug that into this formula here. Here's what I know. I know that the heat of my product is 50, the heat of my reactants is 200. You guys know that I'm taking away a much larger number than I have starting here. So I'm going to get a negative value. And that negative value winds up being negative 150 kilojoules. Taking that back to table I, and the fact that negative delta H's mean exothermic reactions, that's something you already had in your pocket. So just be aware when we are talking about the heat of reaction, it's really that net difference between product and reactant. Don't be that guy and actually try and calculate the energy difference from the activated complex. That's not what it's about. Delta H is your heat of products minus your heat of reactants. The last thing I want to get into is our catalyst. And you guys will remember talking about catalysts in biology, talking about enzymes and things that help facilitate and speed up reactions. Well, this is no different. But now we're going to look at it through the lens of the potential energy diagram. What a catalyst does is speed up a reaction, and it does it by providing an alternate pathway for the reaction to proceed. So if you think of it like the roller coaster, we started here with the reactants. We used to have to go up to the activated complex, at which point we had enough activation energy the reaction could proceed on its own. But the way a catalyst works is providing the alternate pathway, which is this dotted line here. If you look at that, this was the old activation energy, but once we use the catalyzed activation energy and we take this alternate pathway, which is a shorter hill, you'll notice the energy of the catalyzed activated complex is going to be less than the non-catalyzed. The activated complex now shrinks, and the activation energy with a catalyst is far less, so the reaction happens quicker. To illustrate that concept again, here is if we said, well, what's the energy of the activated complex? We'd say it's 100 kilojoules. What's the forward activation energy? Well, we start with 50. We have to get up to 100 at the activated complex. So my activation energy forward is 50 kilojoules. But if I draw in a catalyst, or if the catalyst takes a pathway that's under that activated complex like this, now I don't have to go to the top of the mountain. Essentially, I could go through it and get from reactant to product much quicker. That changes my activation energy and gives me a much lower one when I have the activation energy of the catalyzed forward reaction. Well, that's about it for me. I want to thank you all for tuning in. Practice makes perfect. Make sure you guys hit the potential energy diagram worksheets for homework. Hit them hard and check your answers to ensure your understanding. If you have any questions, make sure you bring those up in the burning questions segment tomorrow. I will catch you guys all on the flip side. Peace out.
That's all, folks.